We said in the introduction to this week that renewable energy technologies are positioned to become the backbone of a completely climate-neutral energy system. Now we want to look at these technologies a bit more systematically. And in this module, we will start with their costs. Before we do that, I want to get us all on the same page about the technologies we're talking about by briefly reviewing them along with their key features. We definitely need to consider photovoltaics, PV. Its key feature, it is almost infinitely scalable. I can put a couple of panels on my roof, or I can build a desert-spanning massive power plant. Especially rooftop PV has a huge potential because the additional infrastructure required is very minimal. Often forgotten, the other major solar electricity technology, concentrating solar power or CSP. Here we use mirrors, focusing sunlight to create high temperatures and then steam, which drives a turbine with a generator. This makes it very similar to the traditional coal, gas, and nuclear power plants that have been operating for decades the exact same way, heat to spin a turbine. The big specialty of CSP is that you can store the heat and continue to use it when the sun is down. But its big drawback is that the system is much more complicated than PV, so it's more expensive. And focusing the sunlight only works when there are no clouds, so deserts are best for this. There are different kinds of wind power. Some are well established, the large onshore and offshore turbines you see in many parts of the world. Others are only starting to emerge now. Floating offshore turbines, which can sit in much deeper parts of the ocean, further away from land. Perhaps even airborne turbines, floating high up and tethered to the ground with cables. It is a little bit unclear whether those will be commercially viable, but it is quite clear that really small turbines on rooftops or in backyards generally do not make economic sense, unlike small rooftop PV systems. And in fact, the benefit of large offshore wind turbines is that they can be built in very windy areas, far from where they might bother people. Hydropower uses water rather than heat to turn a generator, either directly in a river or with a dam. These potentially massive power plants can also provide massive amounts of power, like this one here in Brazil, but at the cost of massive local environmental impacts. So, in general, where large dams do not already exist, it would be better if we can avoid building them. Finally, geothermal power, harnessing heat from the ground. This is often used just for heating, for which lower temperatures near the surface are sufficient. But to get high enough temperatures to produce steam, which again can drive a turbine to turn a generator, you generally need to go quite deep, up to several kilometers deep, making this difficult and expensive, except in areas where heat is closer to the surface. Okay, let's stop here and consider the 5 technologies we have so far. The 3 on the left are generally considered the new renewables. The other 2, the old renewables, because they have been around for much longer. For now, we'll stick to these 5, and we'll add more technologies to our repertoire later in the course. And finally, we want to actually talk about the topic of today, costs. To do so, first we need to establish a metric to use. A common metric used to think about costs of electricity generation technologies is the levelized cost of energy or electricity, abbreviated as LCOE. The unit is money per amount of electricity provided, so for example, dollars per kilowatt hour. To calculate it, we first take the investment cost spread through the lifetime of the plant, the annualized investment cost, divided by the electricity produced on average per year. How to get the annualized investment cost? Quite simple. It is the overnight investment cost, so what it costs to build a power plant if it could happen overnight, without the cost of obtaining financing over months or years of construction time. And this overnight investment cost is multiplied by the depreciation rate. The depreciation rate, in turn, is calculated from the lifetime of the plant in years and the discount rate. Setting the discount rate can be quite tricky and has a significant effect on the resulting LCOE. And you will explore this by yourself in the exercises. Finally, we add to this any operational costs per unit of electricity produced. This would include fuel costs in power plants that burn fuel. This is just one simplified approach to calculate the LCOE, but the principle is always similar to what I've shown here. Let's look at an example of a single rooftop PV panel with a capacity of 300 watt. 25 years is a reasonable lifetime for this. And we assume a discount rate of 3%, so 0.03. Let's say this panel costs around $500, including installation, which is a realistic estimate. These numbers give us a depreciation rate and multiplied with the capital cost, an annualized investment cost of just under $30 for this single PV panel. Let's now say this panel produces 300 kilowatt hours of electricity on average per year. That is a realistic estimate for a temperate climate that isn't all that sunny, say Germany or the northern east coast of the United States. For simplicity, let's say this panel doesn't need maintenance, so there's no operational cost. Adding all of this up gives us an LCOE of just under 10 cents per kilowatt hour. Now, the LCOE is not directly comparable to the price you pay for electricity because it is a greatly simplified number and a lot of things are missing, like the cost of the transmission system. Nor are we considering how the market actually settles on the price you pay. But it is a good way to compare the cost of generating electricity between different technologies in a standardized way. So now, finally, we can compare some cost numbers for the different technologies introduced above by looking at LCOE data from the International Renewable Energy Agency, IRENA. Once again, I have grouped them into the old and the new technologies. And you can also see why. First, in gray, the range of fossil fuel electricity generation costs is highlighted. We can consider this a kind of benchmark for traditional electricity generation costs. Second, the colored bars show you the range of costs from all the projects around the world that were considered when IRENA made this figure. You can see that the old technologies, geo and hydro, are already at the low end of fossil generation costs or even below that range. And you can see that their cost has gone up through time. There are various reasons for this, including, for example, that most of the good sites to build geo or hydro power plants are already occupied. So building new ones means going to the less attractive sites. The new technologies are where things are really happening, as you can see. All of them started with high costs just 10 years ago, but those costs have come down dramatically to the point where they are well within and even below the range of fossil generation costs. This is an example of technological learning and economies of scale. The more you do something, the better you get at it. The more PV, CSP, and wind power plants that were built, the more industry figured out how to do it cheaply. And as larger and more optimized factories produce more and more units, the cost per unit comes down. This dramatic cost reduction is one of the big reasons why these technologies are now in a prime position to supply massive amounts of climate-neutral electricity globally. So, let's summarize where we have gotten to so far. We will add more to this overview of technologies in the next few sessions. And of course, this is only a very high-level overview to help you get the lay of the land, ignoring many details. In the next module, we will continue this tour by looking at the critical issue, which the cost data we've looked at so far completely ignore: the variability of these options and how to quantify it.